Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. We're actually going to finish off our volume unit today by talking about both the volume and the surface area of spheres. So before we begin getting into the actual formulas, let's actually do number 1 and number 2. Pause the video, a couple of warm-up questions to get our brain in gear, and then we will begin. Okay, so number 1 says find the area of a circle that has a diameter of 13 centimeters round to the nearest tenth of a square centimeter. So we have to know what area of a circle is. Based off of our previous lessons, we should know that that's pi r squared. Diameter is 13, which means our radius is equal to 6.5. Diameter is twice the radius, or radius is half the diameter. So I get A is equal to pi times 6.5 squared. I am rounding to the nearest tenth, and that will be 132.7 square centimeters. That would be the area of this circle. Number 2 says find the circumference of a circle that has an area of 81 pi square centimeters. Round your answer to the nearest tenth of a centimeter. So we got to find the circumference, but we're given the area. Well, let's think about what the formula for circumference is. That's equal to 2 pi r. So we need to know the radius. If we know the radius, we're good. Well, we know that the area is equal to pi r squared, and we know that the area is equal to 81 pi for this specific example. So let's solve this equation for r, then we can substitute it into our pink equation. Dividing both sides by pi gets rid of the pi's. So I get 81 is equal to r squared. Take the square root of both sides. You get 9 is equal to r. Substitute into your circumference equation. So 2 pi times 9, that gives us 18 pi. And it does ask us to round to the nearest tenth. So our circumference is approximately 56.5 square centimeters. So we had to use one equation to solve for the radius and then substitute it into a different equation. All right, let's first jump into some vocab for a sphere, and then we'll start talking about the formulas. So a sphere. A sphere is a set of all points that are the same distance from a single point. Okay, so if you just take a point in space and you choose a number, right? You choose a distance. Let's choose 3 inches. So you can think of, okay, I've got a point right here, almost right there, right here, and I'm going to put a point in every area of space that is 3 inches away from this point. And we're talking in 3 dimensions, right? So not just 3 inches this way, 3 inches this way, 3 inches this way, 3 inches this way, but 3 inches right behind this point. Got to have some perspective there. 3 inches in front of this point, 3 inches to the side of this point. Right, so that's where our sphere comes in. Right, so you have all these points that are 3 inches away. It may look like some are closer, but we're just drawing these with a little perspective. The radius is that distance. In this case, the radius would be 3. It's the distance from the center of the sphere to all the points on the sphere. A great circle, well, that's a slice of the sphere where the radius of the circle is the same as the spheres. A great circle divides the sphere into 2 hemispheres, half of a sphere. Another way to think of a great circle has to be sliced through the center of the sphere. Right? If we look at this example right here, only one of these is a great circle, right? This circle right here, because that's going to go through the center. These above and below Well, they're cross sections, but they are not great circles. They will be circles, but they are not the largest circle possible when you slice a sphere. Great circle, largest possible circle you get when you slice the sphere. All right, let's jump into surface area. Now, this is actually one of my favorite activities to do in class because you get to eat food. You get to eat an orange. So if you want to, feel free to go grab an orange if you have one handy, and you can do this activity on your own and then kind of just join us for the discussion. If you do not have an orange handy, well, we'll kind of walk through what would happen, and hopefully you can kind of gain an understanding of where the surface area formula comes from. So the first thing we do if you have an orange is you would trace a great circle from a half of your orange. You could either slice the orange right through the center to do that, or you could just hold the orange flat. When I say flat, it's a sphere. Just hold the orange on your paper and hold your pencil vertically as you trace around the circumference of the sphere. And they're saying we would, I think they say do 6 circles. We're not going to do 6. We're just going to do 4. 6 was actually more than you needed. I just had you draw more. Then you would peel the orange. And think about what the peel of an orange represents. Right? If the orange is the sphere, well, the peel represents the surface of the orange, or the surface area. So you would then start laying your peels on these circles. Right? You'd have some peels right here. Larger the peels, or sorry, the smaller the peels, the better, because it'll let you fill in all the gaps. And you would see that you would be able to fill just about 4 circles, 4 great circles, with your orange peels. And again, not every, actually no orange is a perfect sphere. Well, I mean, maybe you could find one in nature. I've never seen one. But chances are your orange is not a perfect sphere, so you may have covered, a little bit more than 4 circles, a little bit less than 4 circles, but it would be about 4. So we have to think, okay, if the surface of an orange can fill 4 circles, will that allow us to come up with an equation for the total surface area? Well, we filled 4 circles, so we filled the area of 4 circles. Well, the area of one circle is pi r squared. The area of 4 circles would be 4 pi r squared. Surface area of a sphere is 4 pi r squared. I like doing this example because hopefully it sticks with you. Like if you actually went through the process of peeling orange, well, that represents surface area. How many circles did you fill? 4. The area of one circle is pi r squared. You filled 4, etc. That's where that formula comes from. Before we apply this formula, let's also talk about the volume. One other way, I actually do want to make a point of this. Notice that, because some students confuse the volume and the surface area formula, or they see both and they're unsure of which one is which. The surface area formula, right? Area, the units for area are always going to be squared. The units for surface area, not the units, sorry. The radius is being squared for surface area. You'll see that when we do the volume equation for a sphere, the radius ends up being cubed. That's another giveaway about which is the surface area formula, which is the volume formula. Okay, again, I cannot do this water demo. I wish I could. I like doing it myself. But you're going to have to watch the YouTube video to do that. So click on that link. Watch the demonstration that's going on. What the person in the video is going to do is he is going to try to fill a cylinder with a combination of a sphere and a cone. Maybe it'll take, we actually already know that it would take 3 cones, right? In our last video, we saw that 3 cones fill one cylinder if they have the same height and radius. Well, now we're going to see how many spheres it would take to fill a cylinder. Would it take 1 sphere, 2 spheres, 3 spheres? Would it take 1 sphere, 1 cone, 2 cones, 1 sphere, 2 spheres, 1 cone, right? And the key thing here is that they all have the same radius and the same height. So maybe make a guess. What combination of cones and spheres would fill a cylinder? Make a guess for fun, then you'll watch the video and you'll figure it out. Okay, so we saw in the video that, oops, 1 sphere plus 1 cone filled a cylinder. So down here, I just rearranged that equation. I subtracted the cone's volume from both sides, so I get the cylinder minus the cone is equal to the sphere. Now we're going to do some algebra to show you what the equation of the sphere's volume ends up being. But I want you to remember this relationship, right? This is where we're going to start building our equation from, based on the fact that 1 sphere plus 1 cone equals 1 cylinder. Okay, well, the volume of a cylinder, actually, let me scroll up here so we have some more space to do some math. There we go. Volume of a cylinder, pi r squared times h, minus the volume of a cone, which is 1/3 pi r squared times h. That's going to be equal to the volume of a sphere. Now, I'm just going to simplify what I have on the left-hand side, and then that will give me the volume of a sphere. If I have pi r squared times h minus 1/3 pi r squared times h, well, that would give me 2/3 pi r squared times h is equal to the volume of a sphere. Now you may say, Mr. Fawcett, we're done. We simplified. Yes, but does it make sense to have 2/3 pi r squared times h for the formula for a sphere? What are the sphere's dimensions? Right, if you look at that sphere, what are the dimensions? Well, there's only one, right? There's a radius. Now, it may look like it has a height, right? But you're not going to be given the height of a sphere. It's always going to be written in terms of the radius. So let's think. The height of this sphere, we know that's the same as the height of the cylinder, the height of the cone. But what is the height? What is h in terms of r? In other words, can I replace this h with some combination of r's? R squared, 2r, 3r, half r. What could I replace h with in terms of r? Take a second to think. Well, if I draw this radius vertically, there's 1. I draw it down to the bottom, there's 2. So the height ends up being 2r. So I'm going to make that substitution. I'm going to have 2/3 pi r squared times 2r is equal to volume of a sphere. Now my entire formula is in terms of the radius, which is what I want because that's the dimension they're going to give us for a sphere. Now we can just simplify one more time. I'm going to multiply the 2 to the fraction. So that's going to give me 4/3 pi. R times r squared is r cubed. And that is our volume formula for a sphere. Right, so by doing that demo, we could then set up an algebraic equation, do a little manipulation, and come up with a nice, concise formula for this sphere. So those are the two formulas for today, volume and surface area. Let's now look to apply them. The first two are very straightforward. So we are just going to jump to number 3, another composite solid. So we have a little hemisphere on top of a cylinder, and we want to find the volume of everything combined. So pause the video, find the volume of each of those solids independently, and then find the sum. All right, so volume of a hemisphere, well, that's just half a sphere. So volume is going to be 1/2 times 4/3. Let me just check and make sure. Yep, and we're just doing the surface area of 1 and 2. Just want to make sure we weren't doing it for 3 and 4. So volume of hemisphere, 1/2 times the volume of a sphere formula, 4/3 pi, not on my pen, pi r cubed. So we get 4/6 pi, our radius here is 5 cubed. It does say round to the nearest cubic unit. Since I'm in the middle of my problem, though, I'm going to go to 3 decimal places. So the volume of the hemisphere is approximately 261.799 cubic feet. Let's find the volume of that cylinder. Volume of the cylinder, I'll do that in blue. Pi r squared times h. Again, volume of the base times the height. So volume is equal to pi. Radius is the same, 5. Height is 2. If I punch that into a calculator, that gives me approximately 157.080 if I go to 3 decimal places. Well, if I add those together, and I round to the nearest unit, cubed unit to be precise, I've done that 3 times now. I need to get on my pen. There we go. 419 cubic feet would be the volume of that composite solid. All right, let's finish off with a word problem. We're going to do number 6. It says air is leaking from a spherical shaped hot air balloon at a rate of 26 cubic feet per minute. If the balloon has a radius of 7 feet, how long will it take for the balloon to be empty of air? Round to the nearest tenth of a minute. All right, pause the video. See if you are able to answer this question. Well, we know that air is leaking, but first we need to figure out what the initial amount of air is, right? If the balloon's full, how much air is in the balloon? That's going to be a simple volume equation, right? Volume of a sphere. So volume is equal to 4/3 pi r cubed. The sphere's radius, or the balloon's radius, is 7 feet. So 4/3 pi times 7 cubed. Let's punch that into a calculator. That gives us approximately 1,436.755 cubic feet. Again, I'm going to 3 decimal places because I'm in the middle of my problem. Now it's losing 26 cubic feet per minute. So we got to think, all right, well, how do we decide how many minutes it will take for it to be empty? Well, we're just going to divide, right? If I divide, and I'm actually going to include the units here so you know what our units should be at the end. We know that they're going to be minutes, but let's show you why. So I get 1,436.755 cubic feet. And I'm going to divide by 26 feet cubed, or cubic feet per minute. So the numbers are very easy to divide, right? No problem. Let's do that. Make sure we know that this is a comma. We get 55. This is nearest tenth, 55.3. Then we need to figure out units. Well, I have a feet cubed in my numerator. And then I have feet cubed divided by minutes in my denominator. Well, if I divide a number by a fraction, that's the same thing as multiplying by the reciprocal. So it'd be feet cubed times minutes over feet cubed. The feet cubed simplify, and I'm left with minutes. So that's why my units here end up being minutes, 55.3 minutes. I know you would have known that without kind of showing you the units here, but you take other courses where I'm thinking specifically about chem and chem mainly, where you've got to know how to work and manipulate units, and sometimes it's not obvious what the units of your answer will be. And whenever you're dividing by a rate, like feet cubed per minute, you just want to make sure you know how to manipulate those units as well as the numbers. That's why I did that, even though you may have thought, that seemed pretty straightforward. Why did you need to show me how that worked? I think that's going to do it for this video, though. We've gone long enough. As always, enjoy the rest of your day, and we will look forward to seeing you next time with a brand new unit. I think we're actually going to start our discussion of circles, but not just area and circumference. We're going to go far more in depth. All right, we'll see you next time.